Hey, welcome to another Stormworks video. After being a little bit negative on the game last time, very sort of harsh toned post here, I decided to make a sort of a counterpoint, a fairly positive video. And I've limited ability to edit here. I looked at editing software. Everybody wanted me to mortgage my house basically to get to edit a video. So I'm like, no. I do have a utility on my Linux computer that can stitch things together, do a couple of edits, but I have to like go in and make a script file that tells it how to edit the thing, and that may or may not be feasible. I mean, I can concatenate stuff and maybe do other things, but I have to like figure out exactly which frame to cut and then turn that into a script and then send it to the software, which is not the ideal way to edit. The subject of today's video is railroading. This is intended to be a masterclass level of video, which assumes that you're familiar with the game Stormworks. You basically know how to build a vehicle which can move forward and backwards and basically doesn't blow up, and it basically works. It also very much need to know how to do regular algebra. You need to know and at least have a familiarity with Boolean algebra, and that there are algebraic operations that you can do with Boolean variables as well as regular algebra. We also assume that you don't freak out when we get into bring up calculus concepts. Now, we won't be going deep into calculus today, but you really need to understand what a delta is, a differential or a integral, or what it means to integrate, and so that and I will be. You do need a fair amount of background to really get what I'm saying here. The goal of this video is to bring you up from a state where you can basically build to where you can build some of the best trains in the game, and which is sort of a little bit of a conceit on my part, which I'm basically saying that I know how to make the best trains in the game, which may or may not be true, but it's certainly for you to judge that. Now, I'm up here with a basic little rail car. Somebody dared me to build a lowrider train, so I built this little rail car here. There are three interesting. Like the kiddies will just throw a jet engine on a train and call it awesome. No. There are three basic ways to drive a train. There's the direct gear drive trains. There's diesel electric trains, and then diesel battery electric trains. The diesel battery electric trains are basically electric trains, but they have a diesel engine to generate the power. That's a little bit more advanced. You see the game, the little motors here have like a really, really sophisticated motor controller, which is usually a separate box. It costs like a couple $1,000 to generate either the pulse width PWM or the three-phase, which drives the motor. But in this game, you get that for free, so you sort of tend to use it that way. Now, this car is a diesel electric, and it's as simple as you can get. The only working controller here is this, and all that does is it turns the reverser. Like if the reverser is that way, then the motors are put into 100% forward throttle, and if the reverser is the other way, it's 100% throttle that way. And the way the speed is controlled is through the generator. The throttle is wired directly to the motor here, which will go through the gearbox and generate a variable amount of power here, and which, because of the way the game works, has to go through a battery, which causes a little bit of problems. Over here, you have the the only possible ailment I could have is COVID-19. That's the only ailment which has ever existed in the history of humanity. I mean, it's just the concept of sickness, ailment, and infirmity was not invented until the beginning of this year. Anyway, and oh well. The little charger there is and it takes the residual charge from the battery and then keeps my starting battery fully charged, and that's all it does. The only thing else, I got a little speed sensor here, a little function to make it miles per hour, and then the mile per hour gauge. The traction motors are they have an RPM limit, which equates to about 130 miles an hour at top speed. I would consider them capable of 120 as regular cruising. Usually, when you get a what's called a bogie or a truck, usually the motor is integrated with the truck, and you get a 10-to-1 reduction. Like you get a motor that's right next to the axle, and then a gear which is like that lets this spin at like 1,000 RPM and then turns the wheels at 100 RPM, and that's how it usually works. In this game, you actually have to spin the motor. Instead of a reduction gear, you actually have to boost the gear to get it to go faster, and we'll get into that a little bit later. I mean, right now, we'll just go through the sort of a basic retouch of the basics of driving a train. All right, we take our brake off, we set our reverser, and we're going to go backwards, and then we're going to just go full throttle. There's a little bit of a residual charge in the battery, and that's already accelerating us pretty well. Hit the starter on the motor. All right, our motor is going to be turning it, and we got the throttle limited at 60% because that's as much as the train can handle. I mean, any above that, you're generating more power than the system can actually use, and there's no point in doing that, so we limit that off. Actually, the most efficient for this car is only probably about 51% on this specific build. All right, our basic parameters: rotations per second, throttle, and so everything is pretty happy there, and so the air pressure is slightly negative, so it has to produce a negative pressure to draw air into the engine, but it's a very, very small negative pressure, so our intake is running in quite well. An exhaust, very minimal pressure. We are moving at 105 miles an hour already, and I didn't pull out too far from the station because I didn't want this trip to last very long. And we have here is, so yeah, this will eventually climb up to 130, but we're already approaching the station, so we'll draw our throttle back and then just glide right in. I actually forgot which track we're on. Yeah, it's good. So we'll kill throttle. Wait for this. Yeah. Derailed. Oh well. Let's ignore that. Alright, now we got another. This is a full model based on the design of the EMD GP7 locomotive here. It's not quite finished, but it does work. It is a diesel electric. This one is I'd seen a gear drive train, and it worked much, much better than it had any right to, so I was like, okay, Well, I'll build my own gear drive train. I mean, we got the motor, the output, a spin-up gearbox, the train electrics, and then the rest goes through a clutch, an early version of my auto clutch system. And then it's rigged for a 5-speed. It'd probably be better if I made it an 8-speed, but this is a 5-speed and the 4-speed plus overdrive, and it can use the overdrive and this setup to drive this very obnoxious train up to 270 miles an hour. And I'm like what the? I mean, probably if I worked on the gearing a little more, I gave it a little bit more on the top, I could probably get this up to 300. And I'm like, what the hell? So, but seriously, I wanted to make a much more awesome train. I mean, it's just absolutely as amazing as I can make it. And I started working on the Starlight Princess here. This is a 4-truck train, attempting to overcome the wheel slip issues with more trucks. I was hoping to reach 300 in this train, and it's the most I've ever. It can barely get up to 175, and I'm like, rage, anger. Arrgh. But anyway, let's go through all the engineering which went into this thing, and how everything works. So let's just take it piece by piece. So the first piece, this is one of the 2 truck assemblies that's under there. I mean, I've tried, in developing that train, I've tried several different truck assemblies. Now, having a single little motor here obviously can't turn this wheel. It's an inadequate motor, and the wheels you don't get much from it. Now, my first thought, earlier designs had, okay, well, let's just have one medium motor for each of these. And it turns out that the medium motor is drastically overpowered for the truck. On further experimentation, for normal or for regular speeds, the medium motor will slip the wheels. Well, let's see. And for a single truck, the most you can push the throttle is about 30%. For a dual truck like this, maybe 56, 57%. Absolute tops. For 3 trucks, you can you can push the throttle up to 80%, but you start becoming speed limited. Like you can, I have a 3-truck design with a single medium motor, and that thing goes about it tops out at it tops out at maybe 120, 130 under a medium motor drive. I actually converted that. I tried to take the advantages of the gear drive train to push that thing even farther, and I was like, oh, okay, well, I'll take the electric. I mean, the electric works very, very, very well between 0 and 100 miles an hour. So I'll take that, put it in the bank, and keep it that way. But the gear drive works much, much better than it should at high speed. So I'll take the motor, put it through a gear train, and put it into the truck. Put it down into the truck. So I'm at a crossover speed. I'll take the electric motor offline, and I'll put it into gear drive. Doing that got me up to 180 miles an hour. So, but only 180. And I'm like, well, that train also is a 3-truck train, and it goes 270. What gives? I don't know. Game is weird. But let's take a look at what we have going on here. You have an OR gate, which takes the slip reading from each of the trucks, and so we have we capture the slip reading, whether it's slipping. We have the let's see. Yeah, also we have an overdrive controller down there. That's the one that switches it into high gear to get it faster than 130. And then we have the train wheel. I was trying to get it faster, and since my limiting factor was the wheel slip, well, okay, well, what if I managed the throttle very, very precisely? Could I get past the wheel slip? No. It's a hard limit, which seems to be affected most by the weight of the train. It does not has all my attempts to streamline and make this aerodynamically as pure as I could possibly make it, and was utterly in vain. It just has no effect. So again, rage, frustration, and anger. So let's deep dive into this. What makes this tick and what it can do. It has a power takeoff port. So if I put the reason the battery is on the truck here is because the battery is heavy. So either I put the battery on the chassis, which has to be mounted on the pivot, which goes to the wheels, or I could mount the battery below the pivot, and I would have the weight of all this stuff down in the truck below the pivot, so it's a little bit stabler, and it's just a better design. So that's why it's this way. Now the pivot has a power takeoff, and I can use that to power the third truck, or I could have the motor. I could have the motor and have a switch, and then drive power into the truck and drive it that way. So I have a lot of options there. That's all right. Now what I have in the overdrive. Let's edit this. Let's dive down in the logic. Now, what do I have? I'm controlling it with an SR latch. That's just it's basically a 1-bit memory, and I can either set it or I can clear it. Now, the rules for setting the latch is if the speed is above 100, this is 100 miles an hour, it sets the latch and it goes into the overdrive. Now, when it goes into overdrive and it just suddenly switches over, the wheels and the shaft of the motor will be out of sync, and there's a little bit of inertia there. So that will cause the wheels to slip, and then very, very briefly, and that will slow the train down momentarily. So I can't just have a greater than there. I have to lock it in the overdrive mode, and this like 95 miles an hour, about there. So as long as it doesn't slow down below 95 miles an hour, it will hold the overdrive, and you can push through to 170 or wherever your design craps out. So that's how that works basically. There's nothing here. I mean, you got the track speed, either forward or backwards, and then this is greater than that, you go forward, and then I just used less than because it makes the pattern here beautiful and beautiful, well arranged, beautiful layouts there are easy to read and easy to understand, and it's just how you should, and just it's the same principle as writing using a text formatter when writing C or any other language. So that's that. Now the train wheel slip. I mean, our two parameters this is how fast it'll and how fast it'll move, advance the throttle, and then when it starts to slip, that's how fast it'll retreat from that throttle. So, like when it starts to slip, it'll immediately cut the throttle by point and 4%, and basically the this circuit is it's not so simple, and this circuit is. I mean, all of this updates at 60 times a second, so the actual deslip function is very, very fast. It let's see now, the throttle number. Basically, all right, you get the throttle. We care about the we're not passing the throttle. Well, let's see. What are we doing with the throttle? We're taking the throttle, and we're separating out the magnitude of the throttle, and then the direction of the throttle. So we're setting the direction of the throttle aside, and then we are using this multiply and this to reapply the direction of the throttle before we spit it out. So we can ignore. So we're basically dealing with that. That's our and everything from the memory register up to there. Now the memory register, that is the state of the output that we're putting out to the wheels. So, and then all of this is and because it has a memory register, this is now a sequential circuit. It's not a feed-forward circuit. It actually, I mean, it has a state. It changes over time. So it's a sequential circuit. Now, what we let's see the throttle. I mean, once we have the magnitude of the throttle, and it's if the throttle is greater than what we're currently putting out, the throttle signal, the input throttle signal, actually dies right here at this boolean. That's and all we care is, do we want to go? Does the operator of this train want to go faster than we are already going? So that's the question. So, all right, we want to go forwards and we need to accelerate. So yes, we need to accelerate. So what we do is instead we take the throttle from our upseek increment. So we advance the throttle by 1%. So whatever the throttle, we take our current setting, we use this add. We add 1% to our current throttle, and then we switch that in. So there we go. Alternatively, if we want to slow down, now we don't mess around when we're slowing down. When we're slowing down, we take whatever the operator of the train wants, and we bypass all of this, and we send it straight into the switch box. And so like if you're going at 20%, you cut to 10%, it immediately, unconditionally sends that through the circuit. So, and there is that. Now we get to this the next circuit. Now this circuit subtracts 4% from whatever the throttle is. Now, when we're slipping, we subtract 4% from our throttle, and we hopefully recover from the slip. Should probably put that there, now the brake is a special case. Now, if we're braking and we need to slow down, I mean, again, that's an override condition. We override, the brake overrides everything else, and it clears it resets the memory to 0. So if we want to slow, if the operator goes to slow down, he will just we'll just ignore everything, bypass everything, and and basically kill traction immediately. We're slowing down. I mean that's how that works. So and then we go to we have this. We have the direct for forward, and then we have a multiply by -1 for reverse, and then we're out throttle. That's the train, the de-slip. I just pick cute names for things, so this is the deslipification circuit. So I was messing with it, so I'll just go ahead and let's see. All right, so let's. Yeah, I've been stealing a lot of designs, so I'll just. All right, let's go back to where we were. All right, now we have one of these. Now these electric motors here, they're monsters. I mean, like they can drive you could drive a ship with that thing. It's crazy powerful. The problem is that at full blast, that thing takes 800 units of power. Now, all right, so if we have if we have 2 of these under our train, and each of them can take up to 800 units of power, and we have a like 10 coach cars behind us. All of them have lights and stereos and hair dryers or whatever, and the people are using. So so we need more than 800 units of power here to drive our train. So the next part we have to examine is how we're going to generate power for this thing. So I have a little demonstration lab up here. So let's go here. Alright, the first lab we want to look at is, let's see, yeah, I think it's this one. Okay, let's take a look at this one. This gearbox, this lab is optimized for maximum power. So we just have a this is a laboratory on the engine setup. Very important. And from here we take the sum of the generators, and then we have a just the basic stuff back here. Now the only interesting controller here is the fuel economizer. Let's take a look at what the fuel economizer does. All right, let's take a look at this. All right, let's see. What it does is takes the fuel quantity. It then measures how much the quantity of fuel changed, which means that's exactly how much fuel did we use. The delta function, the only trick to the delta function is that this is updated 60 times a second. So, and for the for this to work, we take the so we take that. So that's 1/60th of a second, and for our purposes here, and we just compute the efficiency per unit power. There's a slightly more complex version of this on the gear drive train. Let's actually look at that. Uh, uh, let's just go to a different terminal just so we can look at that train without messing anything else up. The Crimwind and they got me onto a number, inspired me to do a number of things. He likes to measure fuel economy based on quantity to go 100 km, 100 kilometers. So fuel quantity over 100 kilometers. Now, the way he computes the fuel usage is he uses a memory register. Like, he'll record the quantity of fuel in the tank at one instant, and then wait about 4 seconds to get the quantity of fuel at 4 seconds later, and therefore he can only update his display every 3 or 4 seconds. Mine updates continuously because I use that delta function, and let's see, somewhere in here there's a version of the geared. Let's see, stealing a lot of stuff from the game files. Alright, let's see. Now the test version of the gear drive train uses, let's see. Now this this version of the economizer, I think this is a slightly newer version. This one, again, uses a memory cell. Now, what we do here is we're recording when the fuel quantity comes in, like it'll read like 1,000 gallons, 999 gallons, 998 gallons. So that's a negative number. The delta is negative, so therefore we have to make that a positive. Now we put this in here. What we do here is we take where we have a memory register. Now this memory register is the quantity of fuel that we've used over 1 second. How we do that is by doing this. We take the fuel quantity that we're using per second, and then add the value we just read. So we now have 1 second and 1 second plus one time slice of delta. So practically speaking, in rough terms, 61 ticks of fuel consumption. Now we want to report 60 ticks of fuel consumption. Now what we could do is we could record 60 different fuel values and then cycle through them. Now that's not really practical here. So what we do is we decay the memory register at 60 over 61. So this decimal here, this little tiny decimal, is roughly equal to 60 over 61. So we do, when we decay the memory register like this, so instead of, so on this pin right here, we have 60 seconds, or 60 time slices of fuel usage, where, so when we look at the parentheses here, that's 61 time slices of the fuel usage. Then we decay it by that number to get the 60 time slices of fuel usage, which is equal to 1 second of output. So, and that is units per second of output. Now, we can also take this value and so that is our unit of consumption. We can also measure the how much power we're actually generating, and when we do the division here, we are outputting the how much power versus the units of fuel consumption. We also capture the like if it's off and we're not generating generating fuel, we don't want to go into an error state, so we just output 0 in that case. So we do use the divide by. We do protect ourselves by that. So this will either be 0 or some reasonable value for units of power divide by units of fuel, and that's computed by our delta, which is in units per second. Now, the seconds here on our unit, this value is some quantity multiplied by units over seconds. So our numerator is our unit of power as measured, as provided by the game. The unit in the numerator and the denominator. Yeah, the numerator is the units of power. The denominator is units per second. Now let's see. So units fuel are the liquid quantity under the units power. Now the seconds, actually, that because that's you got like a fraction inside of a fraction, so that actually turns into power seconds, which is equivalent to there's kind of, you have to think about it this way. There's instantaneous power, like a voltage times current is power. Now, when you multiply power times time, it becomes units of energy. So that's measured in joules. So literally here we have, and that's actually, so here my label is not quite correct. It's units of energy over units of fuel. So we're literally computing how much energy we are producing from a unit of fuel. So I just had to explain that because it's, some people it's not completely well understood. So that's how that works. And then I have like a bunch of other stuff. And like with this, I was doing experiments to try to make an actual let's see, that's the master slave, to actually make a cruise control for this thing, but that's beyond the scope of this video. All right, back to our laboratory. All right, let's go over here. Let's produce some power. All right. Alright, let's throttle this baby up, see what she does. Let's see, yeah. Alright, 475. Let's shift this into high gear. Yeah, something's going on here. It's not behaving like it should. Alright, I'm summing that. Summing power comes in. It's going into the yeah, I was I was just reading the wrong panel. Okay, you throttle this baby up, and we produce 916 units of power. And in this other gear, let's flip this over. We produce 612. Let's run it at the 900 units output. Okay, so that's pretty good. We're getting 917 units of power. Our RPM is 1300 and 1300, which is not stable on these engines. The highest stable RPM is 1200 for this type of cooling. There are two types of cooling. There's radiator cooling like this, or when you're out in the ocean, you can exchange on the water with the outside and with outside the vessel. And I call that open loop cooling. Those are the two types of cooling. Crimwind runs his engine so gently he doesn't actually blow up. I mean, he just ran out of fuel. It's only got minimal fuel. But yeah, if that had been running long enough, it would have exploded. So this bench is optimized for maximum power output. Let's respawn this again and take an even closer look at it. And let's this time, instead of looking at the power output, let's look at our efficiency. So we'll go back up to the setting we were at, the 900 units power output. Even though it's not stable, our efficiency is measured by this. We're getting 512 units on the power per unit of fuel. So, all right, 5,012, 5,013. And let's just let that blow up and ignore it. Okay. That's an interesting result. This bench is optimized for fuel efficiency. It is designed to get the absolute maximum fuel efficiency. Now the engine the gearboxes are intended to very heavily load the engine. It can only run at full throttle. So if you want to put this into design, it has to be an on-off controller. You can either go full throttle or not at all. So like you'd set it up to say, okay, well, I'll switch it on when it gets to 90%, and I'll run it up to 98% and switch it off, and that's how I'm going to control it. We're only producing 340 units power output, and our efficiency is not reading very well. Let's see again, we have the fuel economizer. Let's just, I thought I'd set this up. Let's adjust this. Let's take off the Alright, just try this, see if this works a little better. As you can see, I mean, I did set this up before. I mean, I took all the designs out of my library and I set them up to run, but I didn't get everything completely debugged. This... see what's going on back here. Maybe I have a different version of the calculator back here. This is annoying. I mean, I'm gonna have to. I think this one got the legacy version of the or here I was doing it straight up instead of by, yeah, this is the old version, so I'll load. Alright, so we got the power output, the fuel quantity, the units per second. Yeah, I think that's equivalent. Alright, let's it's not going as smoothly as I thought. Alright, let's see if this still works. Okay. So here we're getting, as the RPM goes way up, our output is only 84 per, whatever that's computing. On this one, this one's run out of fuel. Let's get this, let this settle in a little bit. It'll take a little while for it to settle in. This one is producing 580 units of power over that, so it's roughly 7 times more efficient, I believe. Or last time I investigated this, this one is like 7 or 8 times more efficient than that one. So we really, we don't like how this works. I mean, it's an on-off generator, and it does not produce much power, but it's much, much more efficient than that one over there. So, what do? So, what I came up with, let's just go straight into microcontrollers. This was again inspired by Crimwind. Crimwind is the guy who used a controller that worked kind of like this. This is a distillation of Crimwind's design, which I believe would. I mean, his design had like everything including the kitchen sink, in one Gonzo controller, which is not how you want to do things. You want, if something's a separate circuit and doesn't connect with anything else, then it needs to be in a separate microcontroller. If it does something that's distinct and unique, oh boy. All right, well, let's see how I explain this. Now, let's start out with what the state is. The state is controlled. We got this up-down counter, and I think we also have an SR latch. What we do here is we get the engine RPS. The ignition control, we'd use that as the reset. So if the ignition is switched off, we reset our latch and we reset our counter. So any controller which has state and that has a memory that's a sequential circuit and anything this complex is going to go haywire. It's going to find a way to go out of control. So therefore, we have a reset function. So when we turn it off and turn it back on, everything is set back to its default state. We also look at the throttle setting here, and that tells us what we're doing. I don't remember exactly how this thing works, and the output and our output control here. Now, what we do here. So anyway, so what we're doing is I don't know. I think when this is in the low state, we're in the the bottom mode, and if it's in the high state, we're in the top mode. When it's in the bottom mode, what it is doing is, we want our engine to start, we want it to idle, and we can't put it at its full. We can't put all the gearing in because it'll stall. We have to run it at a low gearing state, which is for this type of generator, it's a 2-to-1 gearing. So we're in or a 2-to-1 spin up gearing. So we take whatever our RPS is, we multiply by that by 2, and we put it in our generator. This is a fairly mild load on the generator. The engine can usually idle at 14 RPS or 14% throttle, which is acceptable, and that's how we start the generator. We allow the RP when we want to start generating power, we throttle up the engine until we get the power we need. As we do that, we rapidly approach our magic number, which is 7.5 RPS or 450 RPM. And okay, that's good. That's highly efficient. We're generating power, and we're at an efficient setting. But we want more power, and we don't want to lose efficiency. What we do then, as we go past a threshold above our efficiency band, we kick one of our gears down to spin up the generator faster, but place a heavier load on the engine. So the engine is still throttled up, but we're forcing the RPS back down to 450. And so therefore we're getting more power out of it, but we're still in our efficiency band for the RPM. So we're basically widening the efficiency band. That's why it's the wide efficiency band controller. Now, as we push forward, we want more. We can kick it down into a second gear and get even more RPS and get even more power, and still stay in the efficiency band. Now, if we want more out of it, we get past the point that we can be efficient. So we're going to have to give up that efficiency and start getting going straight for power. So when it's in the top state, it starts letting the RPS go up, but we do it in a staged way, so that as we leave the efficiency band, we give up our efficiency as slowly as possible. So we have to go way outside. We have to go all the way up to maximum throttle to get fully into a full power mode, and it doesn't. So yeah, it's basically at its very top mode and the very bottom mode. It's in the same gear. It's in the 2-to-1 gearing. At its maximum efficiency mode, it's in a 3-to-1 gearing, and these gearing steps sort of walk it through the 2-to-1, the 3-to-1, and then back down to the 2-to-1 as it's in its maximum. So again, this controller can actually earn you get your efficiency up from maybe the 20 to. Let's see. What's the best way to say this? This controller can earn you about 40% efficiency, and it'll be 40% better than just run everything through the 2-to-1 gearbox and simply throttle it. So yeah, we're doing a lot of work here, but the payoff is there. I mean, it's a good controller. So, I mean, I'm not sure I can explain it any better. I mean, like on the low side here, you're looking at your 8.5 is your upshift. So when we go above 8.5, it shifts to short. Let's see. Yeah, it shifts to a taller step up gear, and then when it's below 6.5 RPS, it downshifts to an easier gear to again get it back up to the 7.5 RPS. Now, when we're up here, we're doing it differently, again we're trying to manage, and we're being forced out of our efficiency band, but again we do it in a managed way, and that's how that works. And then we either upshift or downshift, and that's the web controller. So, all right. So that with that done, let's look at the train. Now, the train is unfinished. The upper deck of the train is not. I mean, it's only roughed in. I mean, I have some ideas about what I want to put up there. I mean, like you get like an engine like this. It's sort of like a one-car train, and then if you want more functionality, you add the cars to it. I mean, it's got it has. I mean, the design motivation was sort of kind of like this poetic simplicity, where it has just the simple statement with very, very subtle accents there. Like it uses the twin mode. I mean, it does have end ramps. So like if I couple it to that, I can open up the ramp here, and then walk between cars, and that's cool. I mean, I started putting that on each of the trains. Like the standard is that the end here has to be flat with that, and then when it's connected to another car, and it has the same standard, it opens to the right. You have the door on the other side becomes the other end of the other railing for the walkway here, and you get in. And again, you get the engine room back here. Is the that create? I just designed that as sort of a nice accent for you to give like a. Anyway, and it's just the design aesthetic I went for this train. The upstairs is just roughed in. I got this is like just a temporary console to move the train. I have the dials to output the. Remember the wheeled and the deslipifier. That's the output of that. That's how I was debugging it. So. And then here is what I want it to look like. I want a nice glass cockpit. I'm trying to design the visual, and I have to figure out exactly what information I want to put on the digital display, where the buttons need to be, and then there's a lot of programming which has to go into it. Then once that's done, I have to find a way to inject the signals into the train's electronics, and that's another problem. I got some ideas how to do that. I'm not exactly sure how that's going to work. All right, let's look at the engine room. Is the only really finished room on the train. I got a little sensor here, so when I walk into it, the lights and the heaters come on. I have I got the traction motor state here. Got the temperature, the system, the throttle. I have the fuel in percentage. That's like percent fuel usage. All right, then I already showed you how it calculates the efficiency, the amount of fuel per second. So that's all the output from the controller there. I'll walk through the controllers once I get into that. I'll walk through all. Actually, next I'll walk through all the controllers here. So this is again the output of there, so I can fire it up, and it's set to hold the batteries at 95%. So it'll start generating power until it approaches 95%, and then it basically backs off and holds it there. So that's that. And, well, I have it spawned in here, so I'll go ahead and give it a run. Take the brake off. This one is just direct throttle, so I don't have a reverser set up for this, which is inconvenient when I want to slow it. I'm just actually got to turn the key on. Alright, now I've throttled it up to 72%, which is more than what the wheels can take without slipping. So I'll take my flashlight here, and you can see, remember the de-slipifier is going crazy here. It's accelerating. You can see it working. It's twitching like that because it's for 60 times a second. The circuit I showed you earlier is detecting the wheel starting to slip. It backs off the throttle, and then because I have the throttle absurdly high, it tries to advance the throttle, and then it hits the slip and backs off. So yeah, it's doing its job. So I can tell by that it's sort of hanging out around 50-60%. So if I back off the throttle to 57%, you can see it's still twitching like that, but it can actually hold that 57%, and it's not slipping. Now, what did I get for that? Well, it's getting 163, 164. Actually back off the throttle a little more, and wait until we get out of the curves here. I mean, like, we're already, I mean, we went from the station all the way up there in just the time it took me to explain the circuit there. So now we're on once we get onto a really straight section, I could probably barely get it. I could probably coax it. Let's see, alright, we're still slipping, so I have to back off the throttle a little more. So you're back at 55%, holding 55%. So with a little coaxing, I can get it up to 170. Best I've gotten is 175. And given how much work I've put into this train, and how much engineering I've put into this so far, I am annoyed. This train deserves to go 200 and 220, 230. I mean, it's just, I mean, like, what the hell? What the hell, Stormworks? Anyway, I mean, I got a little... See, it's humped like that because it has to get over the lower deck there. Sort of sticks up a bit, so I have to get over it with this hump. And oh well. Yeah. The only other thing to show you on this train on the rails, the Starlight Princess was sort of designed for an overnight run up to the north. That was sort of the inspiration, kind of like the Polar Express. And that's so if I set the time of day to about you sort of get the night glow of this thing, and again you go into the let's find a better time. Let's get the let's find a good time. Yeah, get the moon up, get the doors closed. Yeah. You sort of get the inspiration for this thing. It's anyway. So let's see, the workbench is I don't know whether I had left anything spawned here. Alright, let's take a look at this. Yeah, I still have the other truck in there. Gotta get rid of that. Okay. Well, let's just take a look at it mechanically. Let's. All right. So my I do have the truck assemblies, as I already showed you. I have two of them mounted pretty much directly. I have my dual engine generator set up into a large engine. The two standard configurations for a dual engine, for a large engine, you can either have one large engine into two medium generators, or two large engines into a single large generator. Because the generators are separate, each of them has a clutch going into the common shaft there. I don't know whether I technically need the clutch, or maybe only can get away with only one clutch. I don't want to start them up. I don't want to start them up at the same time. They're like if you have a common shaft, you're sort of forced to start both engines at once, and I don't want to do that. That's too much on the electrical system. So what I have is a staged engine starter here. Now what this circuit does is it has a master engine and a slave engine. If the rotations per second falls below some constant number, actually this is a slightly older design, but I think I changed these parameters. So if it falls below one rotation per second, then the engine is stalled and it needs to be restarted. So, and it'll try to restart on the engine, each of these engines. So when it starts up, it'll start trying to start both of the engines, but because it starts the second engine, and because the first engine is starting, it uses the AND gate to prevent starting the second engine. So it'll only start one engine at a time, so it won't overload the electricals. And so even if it has barely enough battery and barely enough charge, it should still start it on this startup, because it's only starting one engine at a time. And once that first engine is turning, it can start generating power, which will allow it to start the second engine. So this is a good, safe way to start the battery or start the engines without, even if the electricals are in a marginal state or underbuilt. And if I should update this, and I should make these parameter settings. Probably this should go down to 3. I like 3 instead of 4 these days. But yeah, that's that's basically how that controller works. Let's see, what other controllers do I have in here. That's the power system controller. That's the brain behind the generators. That is the master controller for the generator. What it does is this takes the state of charge of the battery. All right, we again, because it's a stateful device, it has a reset. So therefore, it has a key switch ignition. It also has that's also to manage shutting down the engine. So it'll idle the engines normally, but when you turn it off, it kills the throttle, which shuts off the engines, which is how you want it to run. What it really cares about is the battery. It tries to keep the battery at a fixed state of charge. So you can set the throttle on the idle throttle. So this can idle it down to 8%, and we want to keep the battery at 95%. The reason we don't go to 100% is it needs a little bit of room to overshoot, and we don't want it to be inefficient. Actually, this is an older version of the controller. I've had this trained for a long time. The newer version actually has a safety. So, like, if the thing tries to overcharge the battery over 100%, it'll kill the controller, and it will not overcharge the battery. Here it's just a basic clamp, so we did keep the throttle on the engine between the idle throttle and full throttle, and then we have the cutout, the keys, the switch off cutout, and then we send out the throttle. Let's take a look. Let's load up the new version and look and let's see. This is the. Let's take a look at this version. Does a bit more. This one has the. This actually keeps the. This is where the logic is. So if either the key is off, or the battery is already greater than 99% or basically fully charged, then we kill the controller, and we don't overcharge the battery. Otherwise, and it's basically the same. And I'm not going to update this on camera, so. Well, let's see. This is I have my greatest contribution to this game. The greatest thing I've ever contributed to Workshop is the auto clutch. This is the oldest version of the auto clutch. It's just a basic function box. Let's go into the controller editor and load what and. This is the auto clutch. Takes the rotation per second input, and it controls the clutch. That's all it does. This is all it is. All right, this one will start engaging the clutch at 4 rotations per second. The rotation rate is 0.5. So at 6 rotations per second, the clutch will be fully engaged. And then as you throttle up to 7.5% on 7.5 rotations per second, you'll be at your efficiency peak. And then at 20 rotations per second, you're at your red line. That's all there is to it. And this is the only limitation on this clutch is if you're driving it in a car and you slam on the brakes, this thing is not fast enough to disengage before it kills the engine. That is the one and only limitation on this clutch. On that generator I just showed you, maybe I would set this to maybe... Actually, newer builds, I probably prefer maybe 3.5. 3, the lowest I'd ever want to set this, the lowest value you'd ever want to go is 2.5. That's the lowest you want to go. Normally, maybe 3.5. Highest... 5, very, very top would be 6, because you absolutely want to be fully engaged. Like you would maybe set this at a 6 and then this at a 1. The engagement rate, well, whatever this is, plus whatever makes this 1.0. So like if you want, this times 2 is 1. So therefore, 1 plus... so 1 makes it fully engaged. So for this, so whatever that is, and whatever that is, it must be fully engaged by 6.5, 7. So that's how you configure that. And basically, if you get something that's not working, or if it has a, God forbid, a clutch lever on the console, and you're like sitting in it, it's got a clutch, you've got a clutch lever in front of you, you're like, gah, just gah. What you do is you go in, you rip out the clutch lever, you take the auto clutch, you just throw it in. You don't look at it. You don't configure it. You don't do anything. You don't even think. You cook this to the motor directly from the motor. Your RPS in. Hook this directly to the clutch. You don't do anything else. You just You just spawn the thing. You just spawn it into the game. You get into it. You turn it on, and you drive away, and it'll work great. I swear. I mean, I swear. I promise you, it works great. That's all you need to do. No lever, no nothing. You see, the trick with clutches is that when they're fully disengaged, they don't use up any power, and whatever power is in the shaft will go to something else, maybe the generator or some other device on the shaft. I mean, you don't care. When they're fully engaged, they don't use any power because it's just a shaft. It's just a connection. It doesn't use any power. It might have some inertia you don't like, but it doesn't do anything. Now, when it's partially engaged, it's basically a normal clutch. I don't know how they actually work in the game, but in real life, it's just a friction surface. So you're wearing down this friction surface, and you're wasting all that power on all that friction, and you're just throwing it away. Like if you get like halfway down, like half of your energy from your motor is just going to friction, and you're pissing it away. So you want this thing fully engaged, and you want this the way this is set up. I mean, let's take a look at this. This is let's see, x minus 3.5. So this is this one starts to engage at 3.5 rotations per second, and it's fully engaged at 4.5 rotations per second. So 4.5 to 20 rotations per second. This clutch uses no power. It's completely efficient, and below that you're not generating any electricity anyway. So it's just this is how it. Now you see, the reason it can idle at 7% throttle is because the clutch disengages, and because the clutch is disengaged, it only takes 7% throttle to hold it there. And when I get in here and I look at this, when I just turn the key, oh, this is it's not even the right train. This is all right. Let's take a look at the. All right. So when I get in here, the engines will spin up. It'll start generating a little power, and then the controller will settle in, and the output goes down to basically nothing because the clutches are disengaged, and the generator stops spinning. Now when I get it out on the rails, it'll spin up. Let me just take a look at this version, make sure there's no other secrets in here. Yeah, let's see. Yeah, here we got the web controller, all the relays, the engine starter, the fueling economizer. Yeah, just a little I mean, I think because I have a heater in there, I need a thermostat controller to. I don't want to burn the heater at full blast all the time. I want to say, okay, well, I want the room to be 18 degrees centigrade, and so I'll only turn the heater on when it's below 18 degrees centigrade, and therefore I don't burn excess power. That's just the donk on the train controller. And then, of course, I'm looking at the truck, which I showed you earlier. I think that controls the lettering. I'm not sure. And that's got a couple other things to control the lighting, and that's the miles per hour, and that's the doors. And then I think I had the proto. This is just a prototype. I was trying to figure out how to do that. I think I figured out I would eventually need to use two luas, one to generate the display, and then a second lua to capture the touch screen and go to the output. So I haven't really done much work on that. So that's not finished. And I forgot what that did. But okay, well let's get this out on the rails and look closer at the actual fuel efficiency of this train when it's rolling. And let's take instead of doing the previous test was mostly a drive system test. This test we're gonna go at a much more reasonable. We'll start the train out under battery power. Right now we're rolling on batteries, just the batteries. We'll roll it up to set the throttle at 31%, and before the batteries run out, we'll fire up the generator, get everything running down here, and see what our output is going to be. Now, because I was using the batteries, it'll spike up to get control of the batteries, and it'll quickly settle in on what it needs to roll at this speed. We're already up on we're already going like crazy out here. So our output, well, let's see when it settles in here. So we're generating about 500 to 600 units of energy, not power, but energy per unit of fuel. Our fuel consumption per second, we're burning about 0.73 units of fuel per second. So we're burning pretty heavily. And our final drive output, I mean, it's kind of fluctuating. The controller is kind of seeking in on the actual output. The system is under pretty heavy load right now, so it's kind of struggling to find the right output, and it looks like it's settling in around. It's bouncing around a little too much, but it's let's call that 450. So we're generating 450 units of power. Our consumption is pretty stable at about 7/10 of a unit per second, and our efficiency is pretty good. So kind of got silly with the spelling there, but yeah, it's. I mean, in the older version of the game, you couldn't just tooltip your state of charge. You actually had to point at it and say. You actually had to have a gauge, and it told you your state of charge. So yeah, I mean so everything's nice and simple there. Well, you can't really read the engines like this, but yeah, everything's pretty ideal down here. I mean, I'm fairly happy with, and at least as far as the generator goes, this is an amazing generator. I mean, they're basically done better. I mean, like let's just show off just the generator. Let's just show off. Let's just go here. Let's go down to Anneal and see what that configuration can do. I mean, this is basically this is a stripped down version of that generator. Let's see. somewhere here. I got, like, you see, I got a bunch of different I make a lot of these on generator labs, and I don't know where the one I'm thinking about went. I mean, there's... Yeah, I think it was this one. I know. Let's see. Let's rev this baby up. Let's see what it does. Oh shit, that's the wrong. Yeah, kill that. Forgot how to use this thing. Alright, let's kill that and wait for that to stop. Alright, let's try this again. Alright. Alright, this is configured. We have two generators, basically exactly the same configuration that was in the train. We got a 2-to-1 gearbox and a large generator, and this produces 1900 units of power, which is crazy good. So I know when I said when we had the dual trucks there, which I said could use maximum 800 units of power each, or a total of 1600 units of power, we have that covered. I mean, this produces over 1900 units of power, so that so this is perfectly capable of driving those two medium motors to full power. Like if you put this into a ship, I mean, this'll drive a ship like crazy. Oops. Big ups. Let's see, what did I do wrong? Yeah, I was running that hot at 9 to 5, not 2 to 1. Alright, let's try this again. Alright, what's my real output here? So at a sustainable rate that doesn't blow up, we can generate 1900 units of power. Or basically, if we have all those gearboxes for the web controller, that actually drops it down to about 1850, which is still very, very capable of... like, if you put this in a ship with the two medium motors, this will run the ship all day long at full throttle. So this is a very good system, very and with the web controller, and it's as efficient as it can get. I mean, at medium throttle. I mean, if you can, you have to find one of those peaks in the 3 or 4 peak. I think yeah. I mean, wherever the web control, you have to pick one of the peaks in the web controller and lock the throttle in there. It can be very, very efficient or very, very powerful, and then really probably do 30, 40 knots of thrust in that thing. So this is a very good setup here. So bottom line, everything I showed you here, I mean, to get really good at this game, you basically have to sit down with just these laboratories and start building these lab setups for a whole, and just build them all day long, and try out different configurations. Say, okay, I want maximum power, and then just tweak and tweak and tweak, make edits, make changes, spend a whole day making the most powerful generator setup you can get. And then, okay, well, alright, now I have this new efficiency controller. Okay, I'm going to roll it and wire my efficiency calculator to that. And, okay, I'm going to optimize that and tweak and tweak and tweak, use on that, come up with different ideas, different configurations, spend all day getting that efficiency number high, and then you go look at other designs, get inspired, say, okay, well, I can combine this, I can make a circuit which switches between this mode and that mode and get power and efficiency from the same setup. Okay, and then you tweak that all day, and then So basically, that's how you get good at the game, and then you basically use for once in your life, use everything all the math and stuff you learned in school, and you can go crazy. Let's see, and I think this lab, I was doing a test on the large motor here, and on this version, I have 3 motors tied into a single large generator, and then I'm taking this large electric motor, and then I'm actually using the wheel as a dummy load on the generator to measure, to see how much power the thing can take. And this thing will basically take as much power as it can give it. You probably need to use 2 of these super setups, or 2 of the setups from the other lab, and the 2 engines into single large motor. Take 2 of those for each large motor in the system, and that'll probably give you a good controller. And let's see, this, and so basically I'm using the power system controller to keep the battery bank at a state of charge while I'm loading it here. And this one, well, I'm not going to run it right now, but this one can generate up to 2,700 units of power out of this. Now you think about it. Well, let's see. I was generating about 1,900 units of power on that one, and I'm only getting another 800 units of power by the 3rd generator. Now, if I just had that into a dual medium, I could generate 900 units of power. So this starts to get a little bit less exciting, because I'm not generating quite as much power with the 3rd generator as I was going to this. Like if I had both of these generators going, I could generate about 2,900 units of power. Yeah, let's see, 2,800 units of power. But with one generator, maybe 2,700 units of power. So I could either save the weight of that generator by you doing it that way. Well, let's see. I would save the weight of that generator and that 4th motor by doing everything with this, or I could get a little bit more power out of using everything on this bench here. So those are my choices. So yeah, maybe the triple engines into single large generator for 2,700 units of power might be better than having the weight of the 4th generator and the 2nd motor. And so yeah, it's just, I haven't really. The problem with ships, the reason I haven't gotten into ships is getting a good enough hull. If I had a really good hull, and I didn't have to spend like 2 weeks tweaking the contouring and tweaking the balance and tweaking the weight distribution, if I had all that done for me, yeah, I could get into ships and start doing drivetrains for ships. But, well, it's... Anyway. And so I think I'm going to call it a video here. I hope at least part of this was helpful for you, or at least it shows you my mindset for designing this. I don't just throw parts on it and roll forward. Actually design it so it works. It has the right gearing to either roll forward and the correct loading. Like if I start this up and I run it at full throttle, it won't blow up because I've optimized it so that the load will hold the motors at 1,900 units at the maximum RPS they can actually handle, and they'll run all day. I mean, they won't blow up. It's stable setting. So I've done all that work. So yeah, that's the point of this. Actually, I found that putting a turbo pump there actually boosts it by about 2%. Okay, it's only 2%. So if you've got like an efficiency setup and you don't need the 2%, then you can take the pump out. Well, the other advantage of the pump is it gives you another way to cut out air going into here. So if you want another way to kill the engine is you turn the pump off and you killed the engine. So that, and in a lot of situations, it's a very good way to kill them, and then to shut it off. Like if you don't want a really complex controller to with a cutout a cutout function, well, you just cut power to the turbo pump and you're done, and that's how you turn it off. And so that's another way to do things. So another little tip there. So yeah, I guess that's it, and that's just me spilling my guts about all the controllers I use. A lot of my trains, a lot of my controllers are available on Workshop. You'll find that each of my designs are just a, like if I want a train to be manually start, then it's just button to start up, and if I wanted auto start or self starting, well, I'll just have my engine starter, and all of them will have the same engine starter. They're starting to get boring for me, and so I'm kind of like looking for different designs, different challenges or different situations that can sort of spur me to make a different solution. Or I'm starting to get into okay, well, how would I and an interesting thing is the cargo pallets. I mean, okay, getting the cargo onto the train, you need a cargo crane, so it has a lot of electricals on it. You can't just have an alternator system. It doesn't spin it doesn't generate enough power off the alternator to run the crane. So you get into a situation where probably a medium motor would work very well for a crane. It has sort of the right amount of power. And then you have a small an auxiliary power unit and a small generator rigged up like I had on the rail car to power all the electricals on the all the winches and stuff you need to make the crane work. So yeah, I mean, you get a system like that. So yeah, it's kind of nice, kind of get it. And anyway, sorry. And my focus was the Starlight Princess and showing you how that worked and all the engineering that went into making it work the way it does, and why it's set up the way it is. And so yeah, and thank you for watching my video, and I hope it helps you make better builds in your builds. So goodbye, and I'll hit the stop button.